Hello, welcome. Today we're going to do a review on Chapter 3 and 4. And Chapter 3 is examining relationships between two variables. The first thing we have to look at is the response variable and the explanatory variable. Typically, the response variable is what we're measuring. So that's going to typically be in the y variable. An explanatory variable is the thing that we're using to measure the response. So that's typically the x variable. I don't know why I'm spelling this out. They're up there. Scatter plot. Scatter plot shows the relationships between two variables. This is the main graph that we'd use if there's two variables. And you'll see number of beers here is my explanatory variable, and blood alcohol content is my response. And you can see that you make a point for every data point in your data set. Remember, whenever you're making this, remember to label both axes. So label your y and label your x so you can clearly understand what's happening. When you interpret a scatter plot, there's a few things that you need to look for. You want to include the direction, form, and strength of that relationship. And each part has to be in context, and the sentence should be in context. Also, if there's any major outlier or influential point, you want to include that as well. So first, direction. Positively correlated data looks like this. Negative correlated data looks like that. Most people understand that. An R value is important when we're looking at bivariate data. This is our equation to find our R value. It's a way to think about this. This right here is the z-score. X minus the mean over standard deviation, y minus its mean over standard deviation. So you're kind of taking a z-score for x, a z-score for y, multiplying them, adding them all up, and dividing by n minus 1. Typically, you're not even going to use the equation in this class because you'll do a linear regression, and if your diagnostics are on, it'll just give you your r and your r squared. But here are some important properties of r that are good to know. There's no distinction between explanatory or response variable. Now what that means is if I take my x and my y and I switch them, that doesn't affect r. R will remain constant. It also doesn't change if I change my variables. If I go from centimeters to inches, r will not change. Also, a good thing to know is a positive r means that there's a positive correlation, and a negative r means a negative correlation. And we have to know that r is always between -1 and 1. The closer it is to 1 and -1, it tells you that it's a very strong correlation, and the closer it is to 0 is a weaker correlation. Also, both variables have to be quantitative. We can't have a gender and grade point average. You can't find a correlation with those because gender is quantitative or categorical. Correlation also does not describe curve relationships, only linear. And we'll get into that as we get into chapter 4. When we're dealing with R, it's just the linear relationship. Also, correlation is not resistant to outliers. So if you have your data set looking like this, and we have one outlier, that'll change your R value quite a bit. Finally, correlation is not a complete summary of the data. You got to look at more stuff than just correlation if you're looking at a scatter plot. Now, I added this slide just to give you some general idea on what correlations represent. A zero correlation, it's hard to tell whether it goes down or up. It's just, we're not clear what's happening here. A negative 0.3 is going down, but it's pretty loose. 0.5 going up, you can see is positive, but still pretty loose. It's getting closer and closer together. This is a moderate to moderate strong relationship here, where a 0.9 starts to be strong and a 0.99, well, it's almost a straight line. Now, a regression line is a line that we use to predict what's going to happen in our scatter plot. Now, our predicted value is known as our y hat, and the true value is known as y. So what we want to do is to find all of the residuals, or how much of an error we have, we take our y value and subtract it from our predicted value. Now, how I like to think about this, let's say if we have data like this, if I would draw a line like this, my residual is always going to be up and down the vertical distance between the line and our point. Now, if it's positive, it's going to be above the line. And if it's negative residual, it's going to be below the line. So if you're wondering if you do y minus y hat or y hat minus y to find residual, just think about whether that point is above the line or below the line. And that can help you determine the answer for that. Now the least squares regression line, now this is a line that if I have my data points scattered out like so, and I have a line going through, if I draw a vertical distance down and make a square out of that, and I do that for every point in my data set, the line that creates the least amount of area in those squares is going to be my least squares regression line, and so on and so on. The least squares regression line is written just like any linear function. There's another equation for slope where you can take your correlation, your R, and multiply it by standard deviation over standard of y over standard deviation of x, and that you'll always get the slope in that situation. One important thing to know is that this regression line always goes through the point x bar, y bar. So there's going to be some point in the middle that's the mean of the x and the mean of the y. So if you have a data set and you want to find one point that you know is on your least squares regression line, you can just take your mean of x and mean of y, and then you have a point that you know for sure. And if you have a point and you can figure out your slope, you can find the equation of your line. Now extrapolation. Extrapolation is predicting values that are outside of your data set. So if you have a data set that goes from 20 to 40, it kind of goes like this, we have no idea what happens at 60. We don't know if this linear correlation is going to keep going up, if it's maybe parabolic and it'll come back down. All we know is what happens between 20 and 40. So oftentimes when you extrapolate, you get inaccurate results. Residual plots are if I plot my x-axis, so your x variable, your explanatory variable versus your residuals, you'll get a plot that looks like this maybe. And where these are the distances above and below the line that our points are in our scatter plot. Now we're going to use the residuals to tell how well our points model a linear situation. If it's scattered like this, we would say that the original data would be linear, or approximately linear. If there was some curve in the data, like this, that is not a good sign. That would tell us that the data probably is not a linear set of data. So this is what we do not want in our residual plot. The coefficient of determination, or R squared, there's an important phrasing here. R squared is the fraction of the variation in the values of y that can be explained by the least squares regression of y on x. And I used to show the equation. You just take your R value that we have earlier, square it. That's typically how you would find it. But more important is for you to memorize this sentence. And not typically do I tell you to memorize something, but this is something that comes up a lot, and they use it, and it's you have to recognize this particular sentence. Sometimes they say the percent of the variation, but if a problem might say 49% of the variation of peanut butter allergies can be explained with something else, whatever. But what they're telling you is that's code for R squared. So if they give you R squared, maybe they want you to find R from it or something else, but you have to recognize this definition. All right, this is important. This right here is Minitab results. This isn't actually Minitab, I don't think. It's some other statistical printout. But it's good to look at this and see all the information we can get. Now this is our y-intercept, where this is our slope. Arm span is our x variable, or explanatory variable, where height is my y variable. And not all printouts will tell you what the dependent variable is. Once we move into chapter 15, if you've already gotten there, you'll learn that this is the standard error for slope. This is your t-value. And this becomes your p-value for a Lin-Reg t-test. Your degree of freedom is up there, also for chapter 15. This is the standard deviation of your residuals and r squared. Now, once we have r squared, we can square root that to get r, and then take a look at your slope to see if it's positive or negative. If it's positive, then your r is positive. If it's negative, your r would be negative. I think that's about all we know or need for this course. Now, interpreting each of these things is pretty important. It's common for AP to say, interpret the slope. So in this situation, to interpret the slope, I would say for every increase in 1 unit of arm span, height increases our slope, which is 0.840424. So this is how we would interpret it. If I want to interpret my y-intercept is what happens when arm span is 0. So if arm span equals 0, height equals 11.5. Now, this makes no sense in this particular situation because I'm assuming this is people or birds or something, and there's not going to be an arm span of 0. And it's not birds because it's arm span, but whatever. All right, R. Your R value we get by square rooting this. Hold on one moment. All right, I took out my calculator and I found the square root of 0.871 is 0.933. So 0.93 is probably good. So if R is 0.93, we can say there is a strong positive linear correlation between our two variables, which are arm span and height. Now our last one it tells us to do is r squared, which is 87.1. So if I want to interpret r squared, I'd say 87.1% of the variation in height can be explained by linear regression with arm span, just like the definition was on the previous page. These are 4 good things that you should know how to interpret. They come up often on the AP exam. All right, now we're going to look up chapter 4. I should have had an introductory slide that said something like chapter 4. And here we're continuing to do what we did in chapter 3, and then we throw in something kind of weird about categorical variables. All right. Now the first part of it, chapter 4.1, talks about the residual plots. Keep in mind that residual plots, we look for any type of curve or parabola to show that the data is probably not linear. And then we look to see if there's any major fans. That we talk about more in 15, but we talked about a tiny bit in chapter 4. Now, I'm going to do one problem just so it's clear how to do a problem like this. Now, if I type in this data, which I already have, into my L1 and L2, to graph the scatter plot, I'm going to just graph the first graph and do L1, L2, and now I hit zoom 9. Look at that wonderful graph. Now it looks like that data probably isn't very linear. So now what I want to do is graph the residual plot. So I hit Stat, go over to Calc. I'm going to do a linear regression. I like number 8 because B is the slope, and that's typically what we're used to. Linear regression L1, comma L2. And you actually don't even need to do L1, L2 if those are the lists that you're doing. All right, here is my linear regression. Once I do that, my residuals are automatically thrown in a list. So I'm going to go to my stat plot, turn it on, and now I'm going to graph L1 versus my residuals. To do my residuals, I hit second stat, go to number 7, hit enter, zoom 9 again, and there's a great residual plot. Now, it's great, not that it makes it linear, it's good because it shows a really clear pattern. So we know that this data could be better described than with a linear pattern. So let's think of something that's nonlinear. So what we do is we log our x variables and we log our y variables. And when I do that, I already have done that on my calculator. I have L1 through L4. The first thing I'll do is do a linear regression with L1 and L4. So this is a linear regression with my x variables and the log of my y variables. When I do that, see my r squared and r are really high. Those are good indicators. And now I'm going to hit zoom 9. And this is my residual plot for log of y and x. So now I'll do another residual plot for L3 and L4, which are the logs of both of them. So first I do a linear regression and see my r and r squared are less on this one. And then I'll do a zoom 9. Well, this is my residual plot if they're both logged. So that's worse than this one. So the best way to represent this with a line is L1 and L4, which is hours and log of number. Now we have to write the linear equation using logs that best fits that data. So I'm going to turn this back on, go back to my linear regression of L1 and L4, hit enter. So this is my data. I'm going to type in my log of y, so that's log of number is equal to negative 0.002 plus 0.2545 times my hours. All right. Now we need to transform this to eliminate the logs. To transform it, I'm going to do 10 to both sides. And 10 to the log of numbers is just going to be numbers equals this. I could write 10 to the negative 0.002 times 10 to the 0.2545 hours. 10 to the negative 0.002 0.995, and we could take 10 to the 0.2545 to get 1.7968, and hours still stays up in the exponent. So now we've converted this to a nonlinear or a exponential equation. Now these we don't need to do. We used to do this in this chapter, but now we moved it to chapter 15. All right, finding the marginal values is, now the second part, like I said before, doesn't seem to fit in with the first part because it really doesn't. But they threw it all in chapter 4. Marginal values are these totals. So filling out the totals here and the totals here. And they should all add up to the total of all of it. I'm going to pause the video while I do this. All right, here are the marginal values that I found. We have the totals over here, totals on the bottom, and then the total 240. Now find the conditional probabilities below. So if we know there's 2 concussions, what's the probability they're a soccer player, non-soccer player, or non-athlete? Well, out of this, we know that this is 22. So 11 out of 22 would be 0.5. 8 out of 22 is 0.36 repeating. And then we have 3 out of 22, which is 0.136. Is it just the 3/6 repeating there? All right. So this is the conditional distribution for having 2 concussions. Now at the end, they talked about causation, common response, and confounding. Causation, one thing causes another. Um, that's pretty clear. Now, the main way we can tell causation is through a controlled experiment. That's your main way that we can say one thing causes another. Many times, when we don't do an experiment, there's lurking variables. That's this variable C. Now, the lurking variable can cause 2 things, a common response or confounding. A common response is something that affects both variables that causes them to go up or down. The common example is heat. It causes ice cream sales to go up, and it also causes murders to go up. Now, you could look at ice cream sales going up and murders going up and see that there's a correlation. And you can see that they do increase together and decrease together. However, that's not the cause of it. Heat is causing both of those to go up and go down. Now, I like to think about confounding variables as something like in the classroom. They're, they're, this variable is affecting y, but it's not affecting x. Let's take improved test scores. Now, if I improve my test scores, maybe uh, I did flip learning, and I thought I have better scores. I must be better. The flip learning caused that. But there might be another confounding variable. Uh, I could have also changed the homework policy. If I change both of these, I have no idea what affects my improved test scores. Was it the flip learning? Was it the homework policy? Was it both? Uh, so, um, so this makes a confounding variable situation. It's confounding. You don't know which one's causing the result. All right, that's chapter 4.